Okay, then I think we'll start. So this is the second of the talks, and I apologize to people for just shifting the talks all over the place. But tomorrow's talk will be at 2:15. Okay.
Okay, so as I mentioned yesterday, this numbering was on some earlier set of lectures that I gave, and I could not manage to now change this PDF file or modify my PPTX file in this environment. So, anyway, so I thought it's best to leave it like that. Okay, so this is the plan of the talk today. Uh, Discovery, measurement techniques, experimental tests, both for short and long times, and then something about the Calvin theorem, its implication for proton decay, and finally the quantum zero effect as probed by the Itano experiment. Okay, so all of us know of the radioactive decay law, namely that the number of atoms that survive at a time t, if you start out with n0 atoms, then this goes like exponential n0 e to the minus lambda t, where lambda is the decay constant and is inversely proportional. I mean, the inverse of that is the so-called lifetime of the atom. So Rutherford and Soddy in 1902 investigated something called thorium X in those days. It actually now has a name, it's 224 radium. And they looked at this law. You can see the time is plotted in days on the x-axis, and you can see that the parent decays in its numbers, and the daughter, which would be in this case, I think 220 radon, that grows. And they could measure this through the typical alpha particles that are emitted. And so they state in their paper, the law of decay of the activity over time in all cases appears as the expression of a simple law of chemical change in which one substance only alters at a rate proportional to the amount remaining. Namely, dn by dt is just minus lambda n. And then you integrate this equation, you get the n equal to n0 e to the minus lambda t. In 1911, Rutherford performed an experiment with 222 radon, also an alpha emitter, and over a range of times extending up to 27 times the half-life. Because the half-life and lifetime are related, the half-life is about 0.7 times the lifetime. Later, some other people extended this to 40 times the half-life. And then this was in the case of radioactive decay of some nucleus. But for fundamental particles, this was also done. I don't have the date and so on, but they extended it for mu plus, mu minus decay, which we know mu plus at rest decays with a half lifetime, I think, of microseconds. They measured it over about 22 half-lives. So these are some of the references. The Rutherford and Soddy looked at radioactivity, and a byproduct of their studies was this radioactive decay law. And these are two papers in Philosophical Magazine. And one example of how this radioactive decay law can be used is that we all know of carbon-14 dating. And this is, of course, used to date archaeological things. So, for instance, wood, which may be part of a door or something, part of a construction, that can be dated to roughly 10 times that half-life. Half-life of carbon-14 is about 5,700 years. So you can extend it to about 55, maybe maximum 16,000 years. You can't go beyond that because, of course, the numbers decrease dramatically. And then also the number to start with is rather small because carbon-14 is not a naturally occurring isotope. It is produced through cosmogenic interaction. And so there is an exchange of carbon dioxide with life, plants, animals, and so on. And that's how there is an equilibrium set up. And but still, the concentration is of the order of 1 part in 10 to the 14 of the normal carbon. Carbon is about 99% carbon-12, 1% of carbon-13. And this is much, much smaller quantity. So you can't go beyond about 55, 60,000 years. I might just say at this stage that it is important to test this the radioactive decay law also from this point of view, that is it valid for such times? Because if it is not valid for those times, then your inference about the date of that will be wrong. Okay. Also, there is a relationship between the intrinsic lifetime and the intrinsic width of a decaying state. So this was pointed out, of course, by Weisskopf and Wigner in these two papers in Site Physics in the around 30. And they basically introduced the decay through a small non-Hermitian component, this one here. So instead of the time evolution like exponential minus IET, you put in a small term here which takes care of the decay. And so this is just put in by hand, and then you try to infer this from other considerations. So the survival probability, of course, would be take the modulus of this and square it, then you get an exponential minus gamma t by h cross, where gamma is the width of that state. If you take a Fourier transform of this and square this, you actually get a Bright-Wigner form. So 1 by E minus E0, where E0 is the energy of that state, the resonant energy, and then the gamma by 2 squared. So this is the famous Bright-Wigner line shape, which was discovered in the context of neutron resonances on nuclei by both these gentlemen. So this is the line shape of a decaying quantum system with the width of gamma, and of course they are related. So the experimental techniques of measuring the lifetime are basically counting for short quote unquote, because some of these times are fairly long, 10 to the minus 13 seconds to 10 to the 9 seconds. It's a pretty long time. Just to recollect, a year has roughly 3 to 10 to the 7 seconds, so like 30 years. So in this period, you can actually measure the decay rate over periods of the lifetime. Yeah?
I mean 10 to the 9 or 10 to the minus?
No, 10 to the 9. So it's a huge range. I mean, so you can actually count the decay. Pardon?
Why did you call it short?
No, I'll come to what is long. Okay, sir. Yeah. So that's why I put a quote unquote on that short. It's not, not short in the normal sense of the word. I just use it here for separating these two kinds of ranges of lifetime. So yeah.
Basic thing. So the number of undecayed nuclear.
Yeah.
It matters for very long lifetime. Right?
Yes. Yes.
So you need enough counts in some interval, let's say a few seconds or minutes.
Yeah. So whatever time scale you are considering.
So it's a combination of these. How many atoms there are and what.
Correct.
And you need a few tens of counts in the window.
Yeah, that's
is that.
So there are two ways of doing it. I'll come to that. One way is, of course, you count it. You actually follow the half-life. You follow the exponential decay. And then you can fit it to an exponential decay term, and that's how you get that. There may be some background. So, in fact, that if there's a slowly varying background, you can either model it or you can measure it depending on the case at hand. And then you can subtract out that background, and then you get an exponential. There might be even a growth and decay, possibly. Then you have to do fitting for both these lifetimes. So there are different ways. But in any case, you measure the decay rate and then you fit it. Now, why did I say 10 to the 9 seconds? Because actually people have measured lifetimes of the order of 50 years by actually counting. So there's an old source, I think it was done at a few places, Argonne, one of the Australian labs. So, say somebody's guru measures it, keeps that sample there, and then the student, when he becomes older, he measures it 30 years later. And so from that, they can get the decay. Now that's quite good. But you can't, of course, do that if the thing is 300 years. You didn't have such thing. So, but you can do, that's why I said about 10 to the 9 seconds is kind of for actually counting over that period. Now, 10 to the minus 13 seconds, of course, means that you have to use special techniques, electronic techniques. And we have now access to very fast electronics. But also you can do so-called centroid shift measurement. You do a time measurement, and if the lifetime is very short but finite, then from a prompt curve, which is due to some delta function kind of situation, let's say complex scattering, you can see a small shift in the centroid of that curve if that state had a lifetime. So you can go down to about 0.1 picosecond. So using such techniques, you can go down to 10 to the minus 30. Of course, if it is few nanoseconds, then it is much easier for electronics. And certainly microseconds and larger, much easier. Of course, there the difficulties might relate to other kinds of background engineering. Long times, the so-called random coincidence background that you have to take care of, estimate that and so on. So, but these are doable, unless in some special case it's extremely small branch. You're having a signal which is 1,000th of the background or some such. Anyway, there are some special techniques which you can allow you to go down to even shorter times, like 10 to the minus 24 seconds, by measuring, for instance, the resonance width. For instance, if there are very broad resonances, you can measure the some cross section, like the degree of the excitation of that resonance, and that width you can use this inversion to get you the lifetime of that state. And the short times up to about 10 to the minus 18, 10 to the minus 20 seconds, that you can get. I mean, there are various techniques. I've just listed a few. So, for instance, Kx rays are emitted in heavy atoms on the time scales of about 10 to the minus 18 seconds. So, if you looked at compound nuclear processes in coincidence with the X-ray, then you can infer about the lifetime on this kind of time scale. There is also something called channeling. If you make a nuclear reaction using so-called channeled particles, then what is channeling? Channeling is if you have a perfect crystal, you can orient your beam in a particular direction, and then this will get small kicks on the way, but it will go a much farther distance than it would normally do if it is randomly oriented. If there is a polycrystalline sample, the charged particle will have a certain range, but you can have 10 times that range if you orient it on a perfect crystal, and that is the so-called channeling technique. So there you can see that if you excite something in the target, then in certain directions you will get these channeled particles coming out. Certain directions you will not, and that depends on the lifetime of that state. If you can come somewhere in between the lattice planes and then go in a certain direction, then it will go along with. So you can look at that, and if it doesn't, if it is very short, then that won't happen, and then it will not get channeled. So there are techniques like this which use channeling. There are also other slightly indirect methods of inferring lifetimes on the 10 to the minus 20 second scale by actually using the compound nuclear or the decay of an excited nucleus. Most of the heavy nuclei decay by emitting neutrons. That's the preferred channel. The neutron doesn't have a Coulomb barrier. Now, by actually counting these neutrons, you can tell what is the lifetime of that state with some model. But there's some. So the Bohr's compound nuclear theory that has to be used. You have to know the level density and so on. So there is some model dependence on that, but at least you can access those kind of lifetimes. And this is used, for instance, to study the fission of very heavy systems, because it has been a finding of the last 20 years or so that when you excite a compound nucleus, you would expect that thing, if it is at a very high excitation, to fission very rapidly. But that doesn't happen. That doesn't happen because the nuclear field doesn't allow this to go through tunneling process very quickly. So it evolves in time, takes time, and in that time, neutrons are also evaporated. They don't have any barrier. Fission fragments, of course, face a barrier. So you can infer about the lifetime of those nuclei by just counting neutrons. So that's called the jargon in neutron clock. So there are many such techniques which can take you down to smaller times than that 10 to the minus 13 seconds. Some of them are model dependent.
So you're saying there's some correlation between the number of neutrons emitted and fission.
Yeah, that's right.
Time for this.
That you can infer a time scale on that.
Why is there the correlation?
Why is the correlation?
Yeah.
Because suppose the nucleus fissions very fast. You don't even have time for those neutrons to be fast. On the other hand, if it slowly oscillates and then suddenly fissions, then there is time and you can measure those neutrons. And how do you measure those? That's a matter of technique. That you look at the neutron angular distribution. So those that are coming out from the fissioning nucleus can be separated out from the neutrons that come out from the excited fission fragments. Because the fission fragments come out with a certain energy. So there is a boost in one direction and a boost in the opposite direction. So you can separate this thing out by doing angular distributions.
So
In coincidence.
measuring neutron always means look for the decay fragment of the neutron.
Yeah, this has to be done anyway. You have to do it in coincidence. So in other cases, such a technique cannot be probably used because the other decay, like suppose you take a light nucleus which can decay by neutron emission, alpha emission, and so on, then the alpha emission is on a similar time scale. So you can't then use the clock. So there, some people have, in some cases, again, it's not a very general method, have used the fact that X-ray filling times. So if you have a vacancy in the case shell, the X-ray is emitted, and that filling time is a very short time. So depending on whether the X-ray is emitted before or after, let's say, alpha emission, the X-ray energy will be different. So you can tell from the ratio of these X-rays what the lifetime is. So some nice techniques that are used. Now, for longer lifetimes, longer than 10 to the 9 seconds. So if it's like 1,000 years, of course, you can't count for 1,000 years. Our lifetimes are finite, so you can't do that. So then what you do is you assume the exponential decay law. You find out what are the total number of atoms. You find out how many are decaying, and then you can infer what is left. Of course, that is assuming the radioactivity. You can't say that I'm also testing the radioactivity. You can do one or the other, not both. So this way, the longest lifetime measured has been in a recent paper. This is a 2019 paper of the Xenon collaboration. They are actually, this one is looking for double electron capture decay, which is a higher order process than the single electron capture. So this depends on whether or not the neutrino is a Lorentz particle or not. So in that context, they just happen to measure this double electron capture, where of course two neutrinos are emitted. This is so-called standard process, higher order process. And they measured a very long lifetime of the order of 10 to the 22 years in 124 xenon. The neutron-rich xenon is also interesting, and that has also been looked at in xenon time projection chamber experiments, where you are looking for the 2 beta 0 neutrino decay. And there also they have found 2 beta 2 neutrino decay as a byproduct. But that's not so interesting, but I just mention it because this is one of the longest lifetime. Okay, the longest lifetime measured in an indirect way is in this experiment, in which actually Ramnath Kaushik was also involved. He had gone for a sabbatical somewhere in the US, Minnesota or somewhere. And I think he pushed for this experiment to be done, I recollect. And they measured the lifetime of 128 tellurium by doing actually mass spectroscopy. So they did mass spectroscopy of samples and so on, and they inferred that this double beta decay half-life, here of course it is again 2 beta 2 neutrino decay half-life, is of the order of 10 to the 24 years in 128. 130 is the more interesting case, which has a higher Q value, and people have been looking for 2 beta 0 neutrino decay in nature or direct nature. Neutrino, I have not yet found any evidence either way. So that has, of course, a shorter half-life, and that is the so-called CURE experiment at Gran Sasso. I think it is still going on using tellurium oxide crystals, so they get a thermal signal there. And if you have 2 beta 0 neutrino, you get a peak in the spectrum at the end point. That's what they're looking for, but they haven't found any evidence for that, so they have just put bounds on the possible decay rate through that channel.
Lifetime is
Pardon?
proton lifetime is
Yeah, I'll come to that. Proton is on the is part of this talk, yes. So no. So this is a finite measurement. The proton decay would be a bound, lower bound.
So you mentioned that one should know the number of.
Number of atoms, yeah.
That's done by just weighing like mass.
Yeah, so you have to, for instance, if you take some sample of, let's say, tellurium oxide, okay, you do a chemical analysis of that, right, and of course, you know that it's tellurium oxide, you know it's natural tellurium oxide. Mass spectrometry of the natural tellurium tells you how much of 128 there is, 130 there is. So from that, and Avogadro number will tell you how many atoms there are. So from that you can infer N0. And then you know the decay rate. So now you can invert that.
So what you're saying, you should know what impurities are there, fairly well before you can do that. That's
No,
why you
the
need
impurities matter only if they contaminate your counting.
No, otherwise, why not? If you're sure that it is pure, then you
Yeah.
can just take the mass of that and then you get the number.
Yeah, that's right. That's right.
Why do you need the mass?
Yeah. So if, for instance, I mean, you might say that it is very pure, but how do you know that?
That's what, yeah.
So you have to do
Impurities, then
an
you-
experiment to show that it is
Yeah.
pure, demonstrate. So that's it. Otherwise, yeah, if somebody else has done this experiment already and given you the sample, you believe him and then just wait. Okay, so one of the, of course, these tests have been going on, by the way, as I said, Rutherford already did this. Yeah.
So how do you measure this decay rate in the lab?
Decay rate in the lab. You just count. Suppose there is an alpha decaying nucleus.
Okay.
And these would have characteristic alpha energies, right? So you count them with a surface barrier detector, gas detector, whatever. You can use different techniques to count those alphas and make sure that they are not coming from something else. And then just count them as a function of time. So, for instance, in some of these MSc experiments, these things are done. For instance, in our training school, we had a tank where you could irradiate using a neutron source, indium foil, and that indium foil became radioactive. And then you could take it out after a certain amount of radiation and actually count its decay. So you can measure the lifetime.
But decay.
So it depends on what the decay products are. You can also do chemistry. So radiochemists are very good at separating these activities. So they can separate out an activity, count that, and of course there is an efficiency involved there. But if you have contaminating stuff, then you have to do something. But if not, then you just count it, and the characteristic alphas, they are good enough to.
But this your decay rate is directly related to your half-life of the.
That is related.
That is related.
Yeah.
So we cannot wait for large life.
No, so that's what I say. So, I mean, in a lab experiment, of course, you can't measure a 30-year activity, right? But you can measure, let's say, tens of minutes or even a couple of hours. You can measure because you can do some counting now. You can come back, have lunch, and come back, and you will find the rate has gone down, and you can count again a few times. You have a few data points here, a few data points here, and fit an exponential. So you might have a background. So maybe next day you come back and see what is the background, and then subtract that out. Then you get a nice exponential.
So
Yeah.
this like for large half-life.
Yeah.
This half-life of particles,
Yeah.
we can increase the sample of the your data, sample of your particles, like
Yeah.
number of particles.
If that decay rate is small, then you have to take a stronger source in order to do it. And by the way, it will be illustrated in this work of Norman, this aspect. That, if you want to also study over a large range of time, for large times, that sample would have decayed, right? So you irradiate different samples, so make some very strong source, which you don't count initially because your detector will be choked. So you keep that sample for later. So when this, short irradiation time, that guy has decayed, then you take the, so I think they irradiate something like 3-4 samples for different periods of time. Then this solves that problem.
How do you find, for example, things like plutonium,
Yes.
where the lifetime is very
Yeah.
large.
Oh, so you didn't come with the first part of the talk. So, let me go back. Sorry. Yeah. So for time scales up to about 30 years, you can actually count. Good. 30 years is the limit because it's done only in a few labs. Because somebody older has to count it sometime. Conditions have to be the same. Nobody should steal part of the source or whatever. and things like that.
So
But-
carbon dating will not go.
so there, in the case of 30,000 years, what you have to do, you have to know how many of those plutoniums are there to start with. You have to assume the radioactive decay law, and you measure the decay rate through its products like alphas or gamma rays.
Very few would have decayed.
Yeah, a few would have decayed.
Very few.
So yeah, so that depends. I mean, that will give you an error measure, right? Suppose I had very weak activity of plutonium and I measure only 10 decay. Then I have a 30% error on that.
I can understand if you start with a sample.
But if it is a big sample, you can count the gamma rays for it.
Yeah.
For instance, if you want to do alpha counting, alphas have a very small range. So you have to make a thin source. You can't have huge activity there. So you might be limited to some extent if that is already a very big.
But you have to assume radioactivity.
Yeah, you have to assume that's it. That is an assumption. Right. So if you want to test it, you have to use some other way of testing. Yeah, that's right. Okay, so Norman, okay, I was just telling you that, apart from Rutherford and some other people who tested this radioactive decay law over some periods of time, I think Goldhaber also has made some measurements in Brookhaven on such things. But in fact, by the way, he put the first bound on the proton decay level. And it's a very interesting bound. He says, if the proton decayed very fast means on the scale of, let's say, I think 10 to the 13 or 10 to the 14 years, then humans would not exist. Okay. So he says, oh, it must be there for at least 10 to the 14 or 10 to the 15. I mean, just from this single fact, he got a number as large as this, quite remarkable. I mean, Goldhaber, of course, was a very remarkable individual. Pardon?
Can you please repeat?
Oh, repeat. Okay. So his argument was the following. Since human beings have existed for so long, and that radiation affects the DNA. So in over a reasonable period of time, there are too many decays, proton decays. We would not able. We consist primarily of hydrogen, carbon, and oxygen. So we put a bound of about this 10 to 30, right from that. So nothing else required. No detector, nothing. Just the fact that humans exist.
That is too bad.
Huh?
But reality, it's too bad.
Yeah, sure. So, I mean, I think he did this in the early 50s or something like that, maybe late 40s. But this is the same Goldhaber who made the neutrino helicity measurement.
Goldhaber, right?
Yeah, Maurice Goldhaber. So anyway, apart from that, I think later, in the modern times, I think Eric Norman from Lawrence Berkeley Lab, he was the first one to address both short time decay as well as long time decay. And this is the kind of scale that he looked at. So using a cobalt-60 source, which can be prepared rather easily in a reactor, and similarly a 56 manganese source also, which can be prepared in a reactor. Both are, by the way, prepared by irradiating 100% isotopic abundance elements. So 59 cobalt is 100% in nature. Similarly, manganese is 55 manganese is 100% in nature. They have large capture cross section, so you can just put it in a reactor, irradiate them. Lifetimes are different, so we'll come to that. Yeah.
So isn't it better to calculate average lifetime than half-life in life?
They are related, no?
They are related, but you can get data for average life, like because you are.
I mean, when you count, you get a, let's say,
In the sample becomes half.
yeah, that's all. I mean, there's nothing. When it becomes 1 by E, that is your lifetime. That's all. There's nothing very different about it. It's just they're related.
No, I was just thinking in terms of the number of particles.
No, that is a different number of particles to start with. How many you have, that will decide what kind of and the decay rate that you can measure. That is a different.
No,
But half-life and lifetime are related.
Lifetime
Nothing.
we calculate. I don't remember exactly, but I think expression we integrate over number of.
No. You look at that from that exponential decay. You can actually take this as an exercise. You can try to find out what is T half and relate it to the lifetime,
Half-life is log.
which is 1 by lambda.
Lambda.
Lifetime is 1 by lambda. You
Log
try to
is
find.
constant. Doesn't matter.
So
So he's talking about some
Averaging, like.
yeah.
What is confidence,
I'll come to that. That's an important part of my talk. Yeah. So the short decay time, as I said, used cobalt 60, and that addressed whether or not the exponential decay law or the radioactive decay law is valid for times. Now you have to scale it by something, and the only scale parameter here is the lifetime of the state. So T by tau, times over which you are measuring this short or long time, is in this case for cobalt, it tests the law at greater than 10 to the minus 4. Long time measurements, they have gone up all the way up to 45. You notice that Rutherford did it up to, I think, 25 or something. Somebody else did it up to 40. He's gone up to 45. The problem, of course, with the long time scales is that just the number of atoms not reduces dramatically. So if you don't have any atom which is going to decay, then what do you measure? So you have to start with a very large number of atoms which are decaying and then count over these long time periods.
So sorry, there you have to think about the statistics in a
so the decay will be governed by Poisson statistics. All that will be there. But, so anyway, that is kind of known stuff.
Yeah.
You will basically probe whether it is following this law or not.
The Poisson
Statistics is part of it. Yeah.
Poisson is assumed for long.
Pardon?
Poisson statistics is assumed for very long, like for a very long time.
Yeah, for the short time there, the decay rate, but there also is governed by it's a random probabilistic.
Yeah.
Okay, so now I have not quite understood why things should deviate at very long time. So I no position to talk about it except to say that there are many papers. I think maybe this would run into hundreds probably, where for different systems, people have estimated, modification of the radioactive decay law with some power modification. So 1 plus t to the power of n, t to the power of minus n. So so I don't understand that, but suffice it to say that, at least what I understand is that it is important to measure at long lifetimes. But the short time is, I think, very important from another.
Sorry, are these different questions? Or I was asking about statistics, whether it is Poisson.
Yeah.
So whether it is Poisson or not, is that a different question than how you modify the radioactive law? Or is that the same thing?
No, not modify the same. Is that radioactive decay law valid at all?
Right.
Is that form first of all correct? And we will come to this Calvin theorem, which says that it is not correct. But at just one point.
Now, is that the same statement as asking whether it is Poisson statistics or is there two different questions? I don't know.
It's an exponential decay. Purely exponential.
It is what happens. So when we say
Anything else is not.
if we say modification of radioactive law, then we will automatically find a non-Poisson.
I'm not sure about that. I mean, it could still be Poisson, but the decay rate could be modified by some other depending on the system. I think there will be still statistics involved. If you count for some period of time, it might be some number, and if you probably fit that Poisson statistics, I think
The question of but it is a very precise assumption.
so but to honestly answer your question, has somebody looked at the Poisson statistics part of radioactive decay? I don't know the answer. It is, I think, assumed that.
I mean, looking some of
and as far as we know, there is no deviation. I don't know.
Definitely. If it is pure exponential, we call it Poisson. Anything else is a modified Poisson. So that's all.
No. So the Poisson distribution actually does not actually come from guessing. So Poisson distribution is, let's say, if you expect
Some mean number.
Mean number.
Yeah.
You expect 10 numbers every minute. Then if you
Yeah, it is
let's say for longer time.
It's a question of independence, right? I mean, there are independent events, random events, then you would get into Poisson statistics. And then you will get exponential decay. So it's one and the same question, right? I mean, okay.
If you say Poisson, the higher moments are also being defined.
Right.
Whereas the first moment is the average.
Okay.
And for this one, the highest are related to the first one. That's the probability.
All the
Long-
points are related to the first one. That's all the difference. But you can have
If you supposing you have somebody E minus T times T to the 4,
Correct, yeah.
That's not Poisson.
And that will
Because the
show,
one there is something like that, you can count.
the higher moments are going to show up at long.
That depends upon which population you have. Some are short.
You heard it.
The case of photons.
Yeah.
Quasar distribution has been observed.
Yeah.
Very clear.
Ah.
So a similar experiment perhaps. They have wanted.
I mean, some radioactive decays we have seen that. You measure for fixed
Time
intervals of
intervals,
time,
the
and the decay
normal-
rate is fixed, and you plot that distribution.
Correct, correct.
And it is Poisson. In fact, we did that by the way, in the Indian experiment. We did that. Yeah.
You can only say that at 45 it looks Poisson, but if I go to 47, I might get a deviation. It's
I mean, I'm not even sure that they looked at the Poisson aspect of that distribution. They just counted it and they followed the exponential decay. What is expected?
Their data, the data itself, we check with.
Yeah, I guess so. But if you have 2-4 counts, you won't be able to say that. But at shorter times,
Sure.
you would have enough statistics to be able to say. Okay, so at short times, this turns out at least. Perhaps this limit is not so stringent because, especially in the context of very rare decays such as double beta decay, or let's say neutrino-less double beta decay, or even proton decay. So there we are talking about measuring things on a time scale which is much shorter than 10 to the minus 4. I mean, it is like 10 to the minus 20 smaller. So in 68, this gentleman, Kalfin from Russia, the then USSR, published this paper. And there are, later, I think this was not noticed immediately. So he has also physics latest paper. It's there. If somebody is interested, you can take it out. Which says that at very short times, the decay rate should be identically zero. Now, that's a very powerful statement. Only thing is that it doesn't say on what time scale it should go over to the exponential. That depends on what system you're in. But on very general consideration that nobody has, by the way, countered this. I mean, this has been there now for what? 5 years, right? And nobody has countered this.
Sorry,
There is also something, yeah.
what principle is it that?
It's just quantum mechanics. Quantum is quantum. So it doesn't use any other assumption. No model.
It's close to Zeno's theorem.
Pardon?
It's close to Zeno.
Close to?
Zeno effect. No, next one you're right.
Yeah, this is the quantum Zeno effect. This is this paper of Mishra and Sudarshan in 77, which says that if you look at the evolution of a quantum state, it will remain in that quantum state. So this is the so-called quantum Zeno. Except that, maybe they're
Just say.
related. Yes.
Sorry, how about, like here you're making a measurement, but there you're not, right?
No, there you have to make a measurement.
There you have to make a measurement. How you say dm by dt is 0? You have to make a measurement.
Well, I could count later on what was the n that survived, right? Then I know prior to that there was no decay. Without making a measurement, I make a measurement later time and.
No, but you didn't know what happened there.
Exactly.
What happened at that early time, you have to make a measurement. Without making a measurement, how can you say?
So I make a measurement late time.
Yeah, but then it could have happened anywhere. It could have
If
happened
I
anywhere.
find n, if I find n, then I can make the first statement. But n not, if I find n not.
They have a very long lifetime.
Without making
Yeah,
a
but you
measurement,
see, the situation is like that. If you consider proton decay, the lifetime is supposed to be what 10 to the, now I think the limit is 10 to the 30 years. And we live in a universe which is only 10 to the 13 or so years old. So, no, not even that, sorry, it's about 30, but 10 to the 10. 10 to the 10. Okay, so on that scale, this is a very, very long time. So when we make a measurement now, it is actually at a very short time as compared to the lifetime. Now, you might argue, what is the time scale, the relevant time scale? Now, I think when such a thing was posed to Sudarshan, long time back by Raghavan, he said, no. Double beta decay is not relevant at all because, after all, 10 to the minus 24 is the strong interaction. So nucleons are moving around, so that's the time scale. So then, of course, if that is the time scale, then you are at a much longer time scale, so the exponential decay loss will be valid. But, I wouldn't buy that number. I think one has to do an experiment. And so, this is I mean, these experiments address that. Now, whether or not we will find, that's a different matter. But I think this has to be addressed experimentally. Okay, so this, by the way, this quantum Zeno paradox, that has been, quantum Zeno effect has been addressed by an experiment of Itano in as early as 1990. And that I will come at the end of the talk.
Also have quantum anti-Zeno.
But
Also have quantum anti-Zeno.
anti-Zeno. Maybe depending on how you kind of interact with the system, maybe you get the Zeno or the anti.
That has also been experimented.
Anti-Zeno.
No, experiment.
Experimentally also. See, essentially, people are there in the room. People are going out. You push the people again and again into the room. Nobody decays. It's always there. So you can enhance it by pulling them out. That's all the anti-Zeno. The measurement is doing only.
Okay, so this is. So this is a very simple-minded, idea that if you want to look at the decay at small times, you look at the time evolution of the quantum system, and for small times, if you expand this exponent, you will find that the survival probability is again at small times it goes like t squared. So there is no t term that cancels you take the square of this. So this delta H is just defined here as the expectation value of the H squared operator and the expectation value of H squared. So at t equal to 0, dp by dt, and this is the this kind of argument is pretty robust. Of course, Khalfin has probably done better. I have not seen that paper. There is a question journal, and I didn't somehow have access to it. But he refers to that in his physics letters paper of 82. And so if you probe this system at sufficiently small intervals, the idea is that just like this Zeno effect, you will stop it from decaying. And this was this argument was used by Fleming in 83 in the context of the non-observation of proton decay, saying that maybe this is because of the Khalfin theorem. And the fact that you don't see decay has nothing to do with whether or not grand unified theories are correct or wrong. It just is something that follows from the Khalfin theorem. Of course, what Khalfin theorem doesn't say is what is the time scale over which the decay rate reaches the exponential. That would be system dependent. So you expect that dn by dt is 0 at t equal to 0. And then at some time scale, you don't know what happens in between, but somewhere later, it should go to the exponential decay. So that's where you have tested and over a pretty large range. So coming back now to this experiment. So it would be nice to push this small time limit. So look for deviations in decay rate in very long-lived systems. And for instance, bismuth, we now know is a 100% isotope, which was thought to be stable, but we know now it decays to alpha. Very low energy alpha, I think something like 3.2, 3.4 MeV, so it is well below the barrier. That's what gives it a very long lifetime. And I think it has been measured only about 10 to 15 years ago, the decay. Then there are other cases of this 2 beta 2 neutrino decays. I mean, I think there are at least now about 20 to 25 such cases. And they all have lifetimes which are very long. Which are actually, they should be 19 or so. There are some with high Q values which are 10 to the 19 years and all the way up to 10 to the 26 years. So xenon is an interesting case, 136 xenon. You saw 124 xenon is double electron capture, 136 xenon is double beta decay. And this has been found recently to be of the order of 10 to the 21 years by this experiment, Kamland-Zen. Kamland was the experiment of a 1 kiloton liquid scintillator to measure reactor antineutrinos. And they modified that to dissolve xenon in the scintillator. So that is called Kamland-Zen, and a pretty large amount of xenon. And that's how they measured the lifetime to be this. They also, the more interesting case is what they are aiming at, but they could only put a bound, a lower bound on the neutrino-less double beta decay half-life of this some number, 6, 10 to 24. Now, at one point, I was a little interested in this, and that's how I talked to Raghavan about it. He also seemed interested, but then we got cold shower through Sudarshan, who said, this should not show anything. And so anyway, I didn't pursue that. But in any case, even if that were interesting, it would be a very difficult thing to pursue because although it is produced, it is very close to the peak fission fragment distribution, mass distribution in a reactor. And so reactor is a source of this 136 xenon. In fact, if I remember right, the total amount of xenon in the atmosphere, a substantial fraction of that comes from both nuclear tests as well as from power reactors. So this is a good source of xenon. So you can, and I talked to also some of the reactor chemists. They said, yeah, it should be possible to extract this one. This is a rare gas. So you can, when you dissolve the used fuel, you can in principle extract this 136 xenon. Of course, the problem is that it also has other radioactive species like krypton and so on. You have to somehow take care of them, but in principle, again, they can be taken care of. But it's a huge amount of effort. So unless such an effort is warranted by the need to look at this exponential decay law on long, short times, nobody would go through that effort. You have to take hundreds of tons of fuel and extract xenon from it, and then do your experiment in a very low background setup and so on. But in principle, it is possible to address time scales of the order of 10 to the minus 21, which are the ones relevant both for double beta decay as well as for the proton.
Sorry, no.
Yeah.
So supernovae won't produce 136.
Supernovae may be producing that, but
Like you say that
rather difficult to extract 136 xenon from there.
No, it will be mixed up in air.
How can, it would take time for that supernova 136 xenon to come.
No, I mean, there have been supernovae, I'm presuming, in this neighborhood long time ago.
Yeah, but even if it is in your neighborhood, the nearest star is about, I think, how many? 4 Alpha Centauri or something.
No,
4, 5 light years. So it would, at the speed of light, it would take you 5 years.
We are,
of course,
we are remnants of
things don't
supernovae.
travel at the speed of that.
We are remnants of supernovae.
Yeah. So
in that sense,
we had,
there would be some
we had billions of years to evolve. So
But this, we are talking about 10 to the 24 years, right?
right. But you can't use that as a source of xenon. You have to use whatever is
No,
absolute.
this is related to your comment that the only xenon 136 is from the
No. What I mean to say on the Earth,
Right.
the xenon that we have, so in the atmosphere, there is a very small percentage. I think it is of the order of ppb or something like that. There is a small amount of xenon naturally occurring.
Right.
Just as there are other naturally occurring. Argon is, for instance, of the order of 1%. Krypton is less.
Yeah.
Xenon is still heavier, so it is even less than. But what I'm saying is that reactor or atomic explosion produced xenon forms a not insignificant fraction of that. So that addresses this, that you produce it freshly, let's say in a reactor, dissolving reactor fuel, that would be on the time scale of year or 10 years or whatever. You take 10-year-old fuel and dissolve it, you would get it on that scale. But you're addressing something which is having a half-life of 10 to the 21 years. So that is the time scale that you're at, 10 to the minus 21, T by tau, 10 to the minus 20. Okay, but this experiment, I don't know if it ever will be done. But yeah.
Why? I presume 136 xenons lifetime by experiments done separately with fresh orbits.
Yeah.
Is that correct?
Yeah.
Okay. Then now you have to do it with non-fresh samples coming from the cosmos.
No, not from the cosmos. You take a reactor, produce xenon. You take naturally occurring xenon in the atmosphere. So you have a mix. In the atmosphere, you have a mix of freshly prepared and old xenon. But if you take it from the reactor, it's all fresh. So now you can compare the decay.
Yeah, so you have to compare the two lifetime.
Correct. You have to compare the decay rates from these two sources of 136 xenon. If there is a difference, that means that the fresh one is not decaying. Or at least the reduced.
Yeah, there's a difference. Decay law is not the same.
That's right. So that is the idea. And I'll not, this is a long statement. Anyway, this is, you can, these slides will be there. So it just says that it is important to test. So Goldberger Watson, for instance, says that it is important to test because this is only one of a discrete set of possible decay laws. And it might be worthwhile to do this. And this is a long time back. I think this text was written in the early 70s or something. Okay, so now let's come to the experiment of Eric Norman. So this was reported in 88. And they looked at basically the decay of a 5.2-year half-life cobalt-60 source. This is a standard source, by the way, used in all labs because it gives rise to these two lines, the 1332 keV line and this 1173 kV line is used to calibrate gamma ray detectors and so on. And this is the advantage that it decays more than 99% of the time to this excited state. This is a 4+ state. It decays through a cascade, 1173 and 1332. So you can look at both gamma rays and they provide an independent measure of the decay rate if you correct for the small difference in efficiency. So what they did is they took naturally occurring 59 cobalt metal, they put it in a thermal neutron flux in a research reactor and counted. After allowing for some cooling, there are some other activities produced and so on. There also there is an isomer here which you have to allow to decay. That's a 10.5-minute isomer, and then you prepare this source, count it in a high purity germanium detector. It has very sharp responses to gamma rays. Energy resolutions are typically of the order of 2 to 2.5 keV at these two energies. So you can very clearly identify how many events you have, decay events, and then you bin it in time, right from 10 milliseconds to 10 seconds, as they did. And then they look for a deviation in the count rate from exponential decay at small times. So they could have fitted with, in principle, any kind of deviation from the exponential decay. They took this form and they have put bounds on both A and beta. Okay. So they count this for different sampling periods and so on, because they have the data in real time, so they can bin it differently and look for such a form. And this was, of course, suggested by some Russian authors in '84, and they took this form. But in principle, that data can be analyzed with respect to any other form factor you might have here. So they concluded that with this, there are certain bounds on this beta and on the amplitude of that deviation. And as can be seen, this oscillatory term amplitude, they can put bounds on that. So basically, it is consistent with exponential on this time scale. What about the large time scale? So manganese 56, as I said again, can be produced by irradiating 55 manganese, which is 100% in nature. So they took a pure metal, 55 or a semi-metal, I think this is a semi-metal, and then irradiated in the nuclear reactor. They made 4 samples. As I said in answer to this question, that you have a very strong source which you don't count now, which you count last. And the weakest source is what you count, and then intermediate sources you count at times. So they had 4 such samples, and that way they could address, the exponential decay law to about 45 times the half-life. So this happens to be, I think, about multiplied by 0.7, there will be 30 plus times the lifetime, 32 times the lifetime. So again, you look at the gamma rays, you have these various branchings. So everything actually goes through this 847 kV transition. So you look again for it in a germanium detector, and you fit this time spectrum. So you can notice that this is done with different sources, of course. In this case, of course, I think they have looked at both the 847 as well as the 1811. 1811 branch you can see is this branch, and so this has about 28%, so that is less intense. So you can see that this is down by some factor. Of course, the source is also different. This could be different sources, the weaker source or the stronger source, taken at larger times. So anyway, by fitting these, you can try to see if it is exponential and look for this kind of deviation. At least that is what they did. You can again you can put any other form factor that you like, and then search for amplitudes with that form factor. So what they did is they fit this 34, so from here to 45 times the half-life, and they find that A is less than 1.5%. So again, there is no evidence for non-exponential decay consistent with the radioactive decay law. And of course, then using these 4 sources, they could put bounds on this amplitude. You can see this amplitude of the order of 10 to the minus 5, 10 to the minus 4. And at the maximum, of course, this is poorer. Initially, this is larger, it's more stringent bound. Okay, they improved on this experiment in an experiment they did about 7 years later, reported 7 years later in a physics letters paper. And in fact, when they reported that 88 result, CVK Baba and I also thought about this and we said, okay, potassium 40 is a good case to look at. But I mean, we were scooped by Norman. Because of course, he was at it already. So we put a proposal to IUAC. We wanted to use the recoil mass separator. So we did some preliminary experiment to show that yes, it can be done with roughly 5 to 10% accuracy. You can distinguish between 40 potassium, 39 potassium. So we are using that as basically as a mass separator for both the irradiated sample of potassium, and we were going to do that, and non-irradiated. But anyway, we did that experiment. We showed that it's possible, but then when we wanted the full experiment to be done, by that time this paper came out, so we were scooped. Okay, so but it's a very nice piece of work. They compared. The idea was very simple. You prepare 40 potassium, which has a half-life of about 1.3 giga-years, 1.3 billion years, in a reactor. So potassium, natural potassium has potassium 39, is like 93% or something. And if you read it, it's a pretty large cross-section for capturing the neutron with potassium 40. So you can produce fresh, quote-unquote, potassium 40, and you can compare that decay rate with so-called old potassium 40, which is been around for a few billion years at least. So they did this experiment, and again they measured the gamma rays, the 1461 keV gamma ray. Incidentally, this gamma ray is the one which is the most troublesome background in any low counting experiment. So one measure of how good your background reduction is to see this 1460 keV of gamma ray. Also, there is another which comes from the uranium chain, 2.6 MeV gamma ray. So if those are under control, then things are probably under control.
This is the potassium that we eat with
Yeah. So the natural. So by the way, in natural potassium, we have about 100 ppm of potassium 40. So we are being irradiated all the time. So we are actually weak sources of neutrinos. But it's okay. There's such a low rate. Just as we are irradiated by cosmic muons, which are about 200 per square meter per second, nothing untoward happens because there's enough redundancy. At least in DNA, there are two of these parents. When one gets damaged, the other can take care of it. So at low levels, it is not actually a problem. So yeah, this is supposed to be there in I think what bananas. Right? Bananas is supposed to potassium. So those who have potassium deficiency are supposed to take.
So this is electron capture. This is not.
No. It goes through both kinds of. I have not shown the full diagram. So it goes through electron capture, in which case it goes to 40 argon. The electron capture means proton number decreases by 1, but it also undergoes beta minus decay, whereby it goes to calcium 40. And that occurs actually much more often. So you see this branching ratio is only about 11%. So 89% of the time it is undergoing beta minus decay. So anyway, so they did this experiment to look for fresh samples and old samples. And again, they found no evidence for that. Of course, they did mass spectrometry to make sure that you actually, when you irradiate, you have produced more of potassium 40. That they ensured. And having done that, then the number of 40 potassium atoms in both these samples, and you compare the decay rates, and they agree to the level of 10% within your experimental error bar. Now, of course, at that time we thought of perhaps improving this by a factor of 2, which you probably would have, but that was not reason enough to go through this experiment. Unless you can improve it by an order of magnitude or something, not probably worthwhile. But they got a 10% result, which indicates the validity of the decay law for time scales, which are of the order of 10 to the minus 10. So it is already a 4 order of magnitude improvement. 6 orders of magnitude improvement over the previous result, their own result. And they counted it for a long time and similarly obtained a. So 4 years is, of course, something like 28 seconds. Followed it pretty long time. So make sure that. So the implications are that the double beta decay searches might be okay because that's a time scale 10 to the minus 10. Dating might also be okay because the dating technique uses a ratio of potassium 40 to 40 argon. And this also might be okay because the variation is less than some number. However, it is not a test for proton decay. So that is where it stands to this day, that we have not tested the radioactive decay law in a time domain which is relevant to the proton decay experiment.
Sorry, so here the number of 40 potassium
Yeah.
that you produce is very few, or it's a bulk sample?
No. So you take a fraction of that sample, put it in a mass spectrometer, and you can get a mass spectrum of potassium 40 and
So this
potassium
is
39.
material. Like
Yeah. So
talking about powder
it would be of the order, I think it would be of the order of a gram, at least a few grams of that.
So how is that?
So let me see. The number might be given here. No, it's not given here. But I mean, if I remember it right, it would be of the order of a few grams of.
How is that okay? Where do you get that?
Potassium 40, potassium is not a very rare element.
Okay, by chemistry.
Yeah, I mean, you can buy it and it's, I think it's not very expensive. What might be expensive is if you want to purify it to 5 nines or 6 nines.
No, we want very pure, right?
Hmm?
We don't want very pure.
No, you want reasonably pure. So I think they would have taken some, at least 4 nines purity or something. So you don't want some other contaminants which will get irradiated and produce a large amount of background. And suppose that is long lived, then that's a problem. So they would have taken care of that. I have not put those numbers here, but I'm sure they would have taken care of that. So you can see this mass spectrum, for instance, here. Again, I don't remember whether this is normalized, but I think it would be normalized. So in the mass spectrometer, you get more of the potassium 40. Okay, this is should be taken up a little somehow. Anyway, you can see at the bottom here, this is 39, which is the 93% of the isotope. I mean, mass number 39 as part of the natural potassium. And this is potassium 40. This is probably a logarithmic scale or something. So you see this, and when you irradiate it, you get about 30-50% more. So that is the so-called, it has both fresh as well as old, and you look for the change in the decay rate. Incidentally, potassium has 3 isotopes, so you also see 41. 41 is, I think, makes up for the remaining 7 mostly. Okay, so now I come to this sheet. So this is the status that exponential decay loss is experimentally measured to be valid in the T by tau domain of 10 to the minus 10 to about 32. T by tau is T by half. 0.7 factor. So, but anything below that, we don't know the answer. We don't also know how it behaves at very long times. And that there is an experimental difficulty because the number of such decay curves are very small. And so maybe somebody will develop a technique of, having laser excitation and looking for it. So you can have, let's say, nanosecond, let's say, state, which is excited by laser, and then you keep looking for it at long time scales, 50 times that, and keep doing that all the time. So maybe there might be atomic physics people who might test it for a very long time. But I think nuclear physics techniques for this beyond about 50 times half-life looks to be very.
So you said T by tau of how much? Like short time.
So short time is about 10 to the minus 10.
10 to the minus.
So that is okay for double beta decay. Like that. Also for dating, some of the argon potassium 40 ratio dating, used for dating. And on the long side, about 30-35 T by tau. Okay, so this Itano experiment, which addresses this quantum Zeno effect, namely if you look at an atom, it doesn't seem to decay. And the more often you do that, you can actually retard its decay or its transition. So they looked at this system of beryllium-9 ions, which are trapped in a penning trap. So you have a magnetic field which makes this guy, this ion, go around in a cyclotron orbit. And then you have electric fields to suppress its motion along the side which is not covered. So circular motion, but in the perpendicular direction it can go anywhere. Then you have an electric field to suppress that. And so this guy remains trapped, this electromagnetic field. And then you can look for its transitions using lasers. So they trap this of the order of 5,000 such ions at a very low pressure, of course, because they shouldn't capture an electron in the beryllium-9 atom. And these are the three, of course, if you have a magnetic field, depending on the strength of the magnetic field, there is Zeeman splitting. But the principle of this is illustrated by this. Suppose you have a RF transition which takes you from 1 to 2. This is not to scale, by the way. So 2 is very close to 1. So you can excite it through a RF transition. Then you have a laser, near visible or so transition that you can excite from 1 to 3. And this is a very rapid transition, large transition. So if you want to know how many guys are there in one, or you can just excite it using a laser and look at the fluorescent radiation. So if you get enough fluorescent radiation, then I know that the state is that the atom is in the state 1. On the other hand, if it has made a transition to 2 using through the RF, then it has gone out of purview of this laser pulse. And the laser pulse won't be able to probe that. And that is an isomeric state. So it will stay there for a pretty long time. So that is the idea. So you using your RF, so the sequence of pulses is that you apply a RF pulse like this, a broad RF pulse, which is I think of the order of time scale is not given, but I think it's of the order of hundreds of microseconds, the order of milliseconds. And you excite this RF pulse. Because of course, otherwise you have to apply a very high power RF pulse. So whatever experimentally they could do, you apply it for a long time, and then it should excite this state 2. Now you look at the so-called measurement pulses, which is, as I said, through the resonant transition between 1 and 3. So if it excites that, you will see a fluorescent decay, and that you can count with the good. So what they did is they first put maybe just 1 pulse in this whole RF interval. Then they put 2, 3, 4 like that. So if you increase this number, I think they did it in progression, geometric progression, 1, 2, 4, 8, and so on. And then you see that the transition actually does it. So you stop the transition. You killed it. So in fact, if you go to the 64 transitions here, then it's close to 0. Okay, there is a table in the next one, which shows that if you looked at this 2 to 1 transition, you observe almost nothing. Okay, it's just 7% of what you otherwise would have thought should occur. So, it goes as you predict using quantum mechanics at these small times, that if you keep observing, you don't observe this transition. That is what the experiment of Itano tells you. You have observed it. Sorry, I don't know, maybe there are other experiments as well, but this is a very well-cited experiment. So
if you don't see a signal, I thought that's because there is nothing in 1.
Yeah. So what he is looking at is the 2 to 1 transition. So nothing is going to 2, because it's all going to 3. And that RF transition should have been excited. So it goes actually sinusoidally. So you would have expected slowly this population in 2 to build up. But if you keep observing it, the t equal to 0 is reset. So every time it starts out at t equal to 0, you observe it, still t equal to 0. Observe it again. And if you do that closely enough, you can never excite this t equal to, 1 to 2 transition. That has been cut. Yeah. Okay, so coming to the end, what I have not covered is the spatial and temporal dependence on exponential. Well, all kinds of things are going on. The people who are looking for whether the exponential decay law is valid, let's say in summer and winter, some Russian fellows have investigated that. And they find that yes, it's the same. But it's interesting that they're thinking differently. Then what I have again not talked about is altering the decay rate. This is of course a much more interesting area. And because we can indeed change the decay rate. So what we learn in school or even college perhaps is that all chemical changes will not alter the decay rate of radioactivity. That's not true. So for instance, the most spectacular example is if there is an electron capture decay and you remove all the electrons, obviously there is no decay rate. So for instance, in the sun, this would affect the decay rate because, and indeed Amlan Ray has done experiments. Of course, you can't go to the sun to do the experiment, but he has taken different solids in which the electron densities are different at the beryllium site. And he has seen evidence of about up to I think 4% or something change in the decay rate. And in some other cases, people have even seen about 10% change. So depending on the environment and depending on the system, very much on the system.
This affects, of course, the beta electron capture decay the most and also it would affect the lightest electron capture decay the most. Beryllium is a light fellow, so it has only 4 electrons. So the 2 of them are K shell. So if you somehow can alter the probabilities of the K shell electron, suppose you have you can put in a metal or something, and some of them have a chance to go in the continuum, and then you have affected them. So things like that. Or in the sun, where you have a plasma environment. Some of these obviously will go.
Anyway, so it does depend on the local neighborhood and on the ionic state. But also,
there has been a very interesting piece of work, I think it was around 2000 or so, by a gentleman in Washington University, near Washington, DC. And forget the name, some size, not size.
I should have actually put that reference, but again, I couldn't alter this text. Maybe I'll put that as an addendum, a separate file. So what he did is, or what he is theoretical guy, what he found is that if you put a beta decaying nucleus in an electromagnetic field, then you can alter the decay rate of forbidden transition. So he took the case of cesium. Cesium-137, I think, is the 3rd or 4th forbidden beta decay. Now, that forbiddenness comes because the beta has to carry away large angular momentum, 3 or 4 units. So, things which go like kr to the power of 12 plus 1, so that attenuates this decay rate. So that's why it is more forbidden. So what he said is that this is forbidden for a free cesium-137. But suppose I immerse it in a photon field. In particular, he said that RF fields are best. Then you can, he even was involved in some experiment. Of course, he himself admits that it's not a very great experiment. But he claims that we saw some effect like increasing the beta decay rate by about 10%. If you immerse it in a 100 kilowatt resonator tank, RF resonator tank, so which is something typical of these radio stations. So the FM and such stations will have such resonators. And so he put the cesium source inside that, and of course outside we know what the decay rate is. You put it inside, it decays faster by 10%. Now he's not very sure of that, but he himself is not expert, and this was not done through some company or the other, which is called RF. So, but he says that this is an interesting idea. Again, it is not a solution for all the radioactive waste that you produce. Only certain forbidden beta decay transition. If this thing is correct, then you will be able to alter the decay. And by perhaps increasing the strength of the field, you might increase the decay rate 10 times. So instead of I think the cesium-137 has an half-life of 30 years, you can bring it down to a few years. If this is correct. So this is something that he had looked at. And by the way, there's a counter to his paper by some Russian authors who said that no, something is wrong in the mathematics. And he put a counter to the counter, and they never answered. So he believes that he's right. The mathematics is correct. And I think physically, at least what I would like to picture it as is that when it is immersed in an electromagnetic field, the beta that comes out, you have to consider the photons in that electromagnetic field. So it's a dressed electron that you have to consider. Then these selection rules can be bypassed because the angular momentum can be taken care of by the photons that are dressing this electron. So that's the way I look at it. I don't know whether it's such a simple-minded picture.
Initial state is not the same.
Pardon?
Initial state is different.
The initial state is the beta decaying nucleus.
No, but it is an electromagnetic field in one.
Yeah, correct. So if that idea is correct, then this is useful for at least some of the long-lived isotopes. It is practical use. So, in fact, I showed it to some guy who good in mathematics. He said, no, the mathematics looks correct. Now, I don't know. Maybe I'll ask something.
Anyway, this is what I didn't cover.
What is the non-trivial math?
Pardon?
What is the non-trivial?
I don't know whether it's trivial or not. I'm not able to follow whether it's correct or wrong. So somebody who is more into this field should take a look at it and see if it's correct. And if it is correct, then maybe somebody should do an experiment. cesium is very easy to produce, to irradiate something in it. It's a fission product. So you can make it very easy. And you can study decay in a source. I mean, there is a standard gamma ray source. You can use it. No counting. There's a single gamma ray between counted, and it's also rather high energy. So you can put it in something, in some container which has RF, and that gamma ray will come out with reasonably good probability. So it's a good case. If it were some 20 kV transition, then you have to put very thin windows and so on. It requires much more care. This is a relatively easy. So actually, he has a set of papers in physical review, but also one in with the Journal of Physics, which somehow Mathur sent me to write a positive facts. So that's the state there. So,
Yeah. So thank you for